Hello, my name is Zhiyu Chen. I'm from the University of New South Wales. And in this talk, I'll be telling you about neutrino invisible decay and lifetime constraint from the CMB. It's based on a work released early in the year with archive number shown here, and it was done in collaboration with Gabriela Barenborn and Isabel Oedengott from the University of Valencia, and Steen Hannestan, Thomas Tran from the University of Aarhus, and Yvonne Wong from the University of New South Wales. So the neutrinos we'll be considering in this talk is just going to be standard model neutrinos. So as we know, there are fermions and there are three generations of them, each corresponding to a lepton flavor of their electron cousins. In the standard model, they interact only via the weak force, but in cosmology, being a technically massive particle, they also consider to be interacting gravitationally. Now, their mass are quite small, but definitely non-zero, as we know from the neutrino oscillation experiments. But at the moment, we do not know the exact value of the mass from experiment measurements yet. In cosmology, now from the predictions of a hot Big Bang, we know standard model particles will be produced thermally. So we would expect neutrinos being standard model particles to have three thermal populations, one for each generation. And they would decouple from the primordial plasma quite early on, as they only interact via the weak force with the standard model particles. So as the weak force decouples, neutrinos also decouple and thus go on as a free streaming species from that point onwards. And having a small non-zero mass means neutrinos go through this quite non-trivial beginning their life as a ultra-relativistic radiation in the early universe, and then slowly transitions to a non-relativistic matter at late times. And they will have an observable impact on the cosmological observables, such as the cosmic microwave background's anisotropic spectrum. Being at the time of CMB's formation, they are a ultra-relativistic free-streaming species, and the CMB's anisotropic spectrum is sensitive to the number of free-streaming ultra-relativistic species at the time of its formation. So the pertinent question is that if neutrinos were to have some beyond the standard model decay process and decayed invisibly, and somehow lost their free streaming behavior as a consequence, then this will be something that we can observe in the CMB, and the CMB data will have a preference for this kind of decay behavior. Okay, so the decay we want to consider is from the interaction of neutrino scalar field interaction or neutrino Myron interaction. And the Lagrangian we're considering here is this Yukawa type coupling, where it couples the neutrino mass state I with neutrino mass state J, and also with a scalar field phi. Now this scalar field phi could be the myrons that arise from the seesaw models for neutrino mass generation, or it could be any other type of scalar particle depending on the model that you want to consider. And just from this Lagrangian, there are several different types of interactions we consider. So the self-interaction, 2-to-2 self-interaction within neutrinos themselves, or 1-to-2 decay with neutrinos. And depending on which cosmic epoch you're interested in, one of these interactions will be more dominant than the other. So as we can see here, at early times at high temperature, the solid line representing the 2-to-2 self-interaction is more dominant than the 1-to-2 neutrino decay. And the reverse is true at late times. At lower temperatures, neutrino decay becomes more dominant over the 2-to-2 self-interaction. So for this work, we were mainly concentrating on the 1-to-2 neutrino decay, where we have a heavier mother neutrino decaying into a lighter daughter neutrino, plus a massless scalar Myron phi. And so as you can see with the dotted line here, the dashed line grows in strength, so this is a recoupling scenario that we're considering. Now, in this 1-to-2 decay recoupling scenario, there are two separate regimes. The first one is the relativistic regime. In this case, the neutrino decay recouples quite early, and while the mother neutrino particle is still ultra-relativistic. And the consequence of this is that the inverse decay process is still kinematically active and allowed. And you can see in the evolution of the neutrino's energy density, so here plot the energy density as a function of time. The blue line represents the mother neutrino's population. And you can see as the decay recouples and it starts producing this green Myron phi scalar field, the neutrino's mother population does not immediately die away, because in this intermediate relativistic regime, the mother population is being replenished by the inverse decay, and it only drops off once the mother particle falls non-relativistic and the inverse decay is kinematically shut off. And so the alternative scenario regime is non-relativistic decay regime, where the recoupling happens quite late, and in this case, the inverse decay is already kinematically suppressed, and you see in this bottom panel here, as soon as the decay recouples, the mother neutrinos population falls off immediately. Okay, so cosmologically, we want to consider mainly the relativistic decay regime because the CMB is sensitive to the free streaming behavior, and the inverse decay is the one that's responsible for redistributing momentum and effectively could cause the neutrinos to lose the free streaming behavior. So if we want to use the CMB to constrain neutrino lifetime, the relativistic decay regime is the focus to look at. So yeah, specifically the CMB's anisotropic spectrum is sensitive to exactly how many free streaming ultra-relativistic species are around during the formation of CMB. And since the neutrinos form a large portion of the relativistic species at the time, their free streaming behavior is tied quite closely to the CMB observables. So if the free streaming behavior is to be lost while the inverse decay is active, then we can say the CMB could have a preference on decay timing and the strength. So if the CMB prefers a effective number of free streaming neutrinos, then it wouldn't want the decay to recouple too early and causing the neutrinos to lose their free streaming behavior while the CMB is still forming. And this could effectively form a lower bound on the neutrino lifetime, and it's been done several times by a lot of different groups in the past. And let's look at what the previous work has been done regarding this relativist decay constraint. So the main focus is around this transport rate quantity. So transport rate describes how the momentum is being transported around the neutrino fluid by the inverse decay process. And we say that the free streaming behavior of the neutrinos is lost when sufficient amount of momentum is being transported around the fluid and the fluid becomes isotropized. So the transport rate has been previously a priori assumed to be the rest frame decay rate and suppressed by 3 powers of the Lorentz factor, this m divided by e factor. The justification for these 3 powers of suppression is that one of them comes from the time dilation of transforming from the rest frame to the cosmic frame, and 2 additional powers comes from relativistic beaming effect. So if the decay happens in a relativistic regime, you expect the daughter particles to be mostly produced in the forward direction. So they're claiming that it takes additional numbers of interaction in order for sufficient amount of momentum to be transported off the initial axis of the mother neutrinos traveling. And this was very first done by assuming an instantaneous switching regime. So when the transport rate at some redshift z star becomes comparable to the Hubble rate, then we assume that the neutrino's free streaming behavior is instantaneously switched off. And it was later refined to be included as a damping term in the neutrino's Boltzmann hierarchy. So you add it as an exponential damping to the neutrino perturbations of L equals 2 and above. So in essence, suppressing and damping the neutrino fluid's anisotropic stress. And both of these has been shown to be to yield similar constraints, the lower bound on neutrino lifetime. And with the Planck data, Akidiakono and Hannestead reported that this lower bound is around times 10 to the 9 seconds with some mass parameter dependence. And what we wish to do is to investigate this from a first principle approach. So rather than a priori assume some transport rate, we just want to solve the full collisional Boltzmann equation and see what the transport rate actually is predicted by first principle Boltzmann equation. So the approach is to solve the equations of motion for the combined neutrino-Majoron fluids anisotropic stress and look at if the equations of motion actually shows some kind of exponential damping. And if it does, then what exactly is the rate at this exponential damping is happening at? And we do make some assumptions to make the calculation tractable. So first of all, we're still assuming that the daughter particles are massless. So both the daughter neutrino and the daughter scalar field phi is massless. And we also assume that the neutrino's background distribution is mostly thermal during the relativistic regime. And also for all of the perturbations of the neutrinos and the scalar field, the perturbations follow a separable ansatz, which means that the perturbation can be separated into a purely momentum part and a purely spatial part. And finally, we also assume a kind of adiabatic condition where the spatial perturbations across all the different neutrino and Majoron species involved in the decay process are the same across all species. So once we solve the full collisional Boltzmann equation, we find that the equations of motion for the anisotropic stress of the neutrino and Majoron combined fluid is indeed a exponential damping. But what we found is that the leading order rate this damping happens at is in fact not the rate that's been previously assumed. So you get a similar transport rate expression here, but rather than 3 powers of Lorentz suppression, you now have 5 powers. And it's quite interesting that the 3-power Lorentz term actually vanishes exactly due to momentum conservation. So the full collisional Boltzmann equation is telling us that during the decay process, in particular the inverse decay process, the momentum has to be conserved mostly along the line of initial travel of the mother neutrino, and very little momentum is allowed to leak out to the transverse direction. And so this tells us that the relativistic decay in the neutrinos actually has a very mild effect on the free streaming behavior because it's so inefficient at isotropizing the fluid. And so the neutrino lifetime from CMB, where it hinges upon the free streaming behavior being lost due to the inverse decay, can now be relaxed to be allow the neutrino decay to recouple much closer to CMB, since it doesn't really affect the free streaming at all. And translating the lower bound for the lifetime with this new transport rate of 5 powers of suppression, we find that lifetime is now much lower at 4 times 10 to the 6 seconds with some mass parameter dependence. And here we're showing the mass parameter space that the old lower bound is shown by this red dashed line. And with the new transport rate, the new lower bound is now down here at this solid red line, and thus freeing up a large region of the parameter space. So in conclusion, neutrino scalar or neutrino maron decay is a prediction of certain neutrino mass models, such as the seesaw model. And if the neutrinos were to undergo some kind of invisible decay in cosmology, their decay lifetime can be constrained as the free streaming behavior is tied to the relativistic inverse decay, and the cosmological observables such as the CMB anisotropic spectrum has a preference on the neutrinos free streaming. And with a full Boltzmann treatment looking at the decay scenario without any assumptions, we find that the actual damping rate or the transport rate is significantly different to what's been previously assumed in literature. And with this new, more accurate transport rate, we can relax the neutrino lifetime constraint by almost 3 orders of magnitude, and thus freeing up a larger region of parameter space for relativistic species decaying and interacting with the CMB. Thank you for your attention.